So we'll be talking about the Moivre Theorem. So where we'll talk about the powers and roots of complex numbers. So previously we discussed a polar form of a complex number, the argument of a complex number, the modulus of a complex number. Now we want to talk about the Moivre Theorem. What is really the Moivre Theorem? So we state that let z equals to x plus I1. This is the rectangular form, that is the Cartesian form. And we say that z can be represented in polar form as z equal to r, which is the modulus of the complex, open bracket cos theta plus I sin theta. So where theta is the argument of the complex number. So this is the polar form, and this is the rectangular form, which is the Cartesian form. Now we want to show that we want to prove that z, which is the power of the complex number z, that if we have z equals to x plus I1, then z raised to the power of n is equal to r raised to the power of n, open bracket, cos n theta plus I sin n theta. This is the Moivre Theorem. That we said if z is equals to x plus I1, then z raised to the power of n is equals to r raised to the power of n cos n theta plus I sin n theta. So this is the Moivre Theorem. Then how do we show this? So we say let z1 to be equal to x1 plus iy1, and z2 to be equal to x2 plus what? iy. Let's switch off the fan. This is what we have. So now in polar form, we have z1 to be equal to r1, right?
Yes.
Cos theta 1, is that correct?
Yes. Sorry.
Plus I sin what? Theta 1. Then z2 is equal to what? R2, right? Open bracket cos theta 2 plus what? I sin what? Theta 2. So this is our z1 and z2. So we now say that z1 times z2 will be equal to this times this, right? So we have r1 cos theta 1 plus I sin theta 1 times r2 cos what? Theta 2 plus what? I sin theta 2. So this is equal to, this is r1 times r1, right? So we have r1, r2. Now this cos theta 1 plus what? I sine theta 1, right? Then times cos theta 2 plus what? I sine theta 2. Now let's expand this. If we do that, we have this is R1, R2, open bracket, this times this will have cos theta 1, cos theta 2, plus I sine theta 2, cos theta 1, right? Plus I sine theta 1, cos theta 2, plus I square. Okay, this is I times I, which is I square, and I square is minus 1. So we have here to be minus, then sine theta 1, sine theta what? 2. So we close this. Then we have R1, R2 to be, then Z1, Z2 to be equal. So R1, R2, open brackets, this and this, right? This is cos theta 1, cos theta 2, minus sine theta 1, sine theta 2. Then we have plus, right? Plus I, open bracket, sine theta 2, cos theta 1, right? Plus sine theta 1, cos theta 2. Okay, yeah, thank you. Now, looking at this clearly, you see that back to our compound angle, you see that cos theta 1, cos theta 2 minus sin theta 1, sin theta 2 is the same thing as cos theta 1 plus 2 plus theta 2. That is, you now have Z1, Z2 is equal to R1, R2, open bracket. This here is the same thing as cos theta 1 plus what? Theta 2. Back to trigonometry, compound angle. The plus I, open bracket. Yes. So this is sine theta 1 plus what? Theta 2. So this is what we have. Now we see that, so we multiply Z1 and Z2, so we have this. Now we say that if we multiply, suppose we multiply Z1, Z2 with Z3, and that our Z3 is X3 plus IY3, and in polar form gives us what? R3, open bracket, cos theta 3 plus what? I sin theta 3. And in multiplying this Z1, Z2, Z3 from this identity, you will see that we have R1, R2, R3, open bracket, cos theta 1 plus what? Theta 2 plus what? Theta 3. Plus I times sine theta 1 plus what? Theta 2 plus what? Theta 3. This is what you have. Okay? So this is what you have, and please. Let me get started. Maybe you pause first. Pause. Let me get this started. You paused earlier, right? Yes. So what we have now is we have this to be this. Now, in general, we have z1, z2, z3 up to zn. Then it will be equal to r1, r2 up to rn times cos theta 1 plus theta 2 plus dot dot plus theta n plus I sine theta 1 plus what? Theta 2 plus dot dot plus what? Theta n. Then close. So this is the general form. Now, the question now is this, that if z1 is equals to z2 is equals to up to what? Zn. So it means now that all the complex numbers z1, z2 are equal. So it means how many of z1 do we have here?
N times.
N times, right?
Yes.
So which is what? 0 to the power of what? N. Right? So which is 0 to the power of n equal to, and if this is this, then 0 to the power of n is equal to, this is r1, r2 up to rn. So that is r is in how many times? N times, right? So which you have r raised to the power of what? N. Then open bracket. So this is theta 1, theta 2 up to theta n. So we have cos theta what? N. But sorry, this is multiplication, right? So this is addition. So how many of theta do we have here?
Look at N times.
N times. So n what? N theta plus I sine here. So we also have what? N theta. Okay. So this is what the Moivre theorem is telling us. So this is the Moivre theorem is telling us that if we have the complex number z1, z2 up to zn, and we're able to get these identities and up to this form, and we say that z1 is equals to zn, then this holds. So 0 to the power of n equals to r to the power of n plus n theta plus I sine n theta. This is actually the power of a complex number. So you can be asked that, okay, to find the value of 2 plus 3I raised to the power of 300. This will give you the answer. Now if you are asked z equals to 4 plus 2I raised to the power of 500, this is what we will use. Okay. So we'll solve one example quickly. So here we have example 1. If z is equal to minus root 3 plus I. If z is equals to minus root 2 plus I, find a 0 raised to the power of 8. B, z raised to the power of 4. 3 raised to the power of minus 4. Solution. So we have our z equals to minus the square root of 3 plus 1. Now, ordinarily, this is our z. If it is z raised to the power of 2, what we simply do is just to multiply this by itself. Z raised to the power of 3, you simply multiply it 3 times. Z raised to the power of 1, so on and so forth. But the question now is, if you add 0 raised to the power of 8, you keep still expanding 0 raised to the power of 20. So, and if it is 0 raised to the power of 3, maybe within 5 minutes you are done. But 0 raised to the power of 20 probably to take you up to maybe 5 hours or so, provided there is no error in the computation. But now, for us to find this or this, we will need to employ the Moivre theorem. First, before we can use the Moivre theorem, then we need to convert this complex number here to the polar form. Yeah. So then, to convert to polar form, we need to find the modulus of the complex number and the what? The argument. So here, the modulus r is equals to what? The square root of x squared plus y squared, which is the same thing as minus root 3 square plus 1 square, and which is the same thing as 3 plus 1, which is what? The square root of what? 4, and which is equals to what? 2. The square root of 4 actually is plus or minus 2. Yes. But since we are talking about distance, so we take the positive value. So the modulus is 2. Then the argument at z is equal to, first, before finding this, now use our tan inverse of y over what? Yes. X. So first, our y is 1, right? Yes. And our x is what? Minus root 3. Yeah. But take note, while representing this in the Cartesian plane, you remember that this is actually telling us the location where it falls in the quadrant. Yeah. Yes. Okay. So, like looking at this now, you see that this is our xy. Then we will have that. This is minus, right? This is your x-axis, right? So this is your minus, right? And your y-axis is 1, which is the positive x-axis. Yeah, this one. Okay. X-axis is minus 3, right? And y-axis is 1, which is here, right? So it means it's falling in the what? Second quadrant. Yeah. Good.
Because tan is negative on the second quadrant.
Tan is negative on the second quadrant. So you can simply say tan inverse of y is 1 divided by the square root of 3. Now, you can, if you indicate your square root of 3, it will take you directly to the second quadrant. Yes. But if you remove it, to give the answer in the first quadrant before you now move down to what? Second quadrant. So, and tan inverse of 1 over root 3 is what? Yes. Is it 30?
Yes.
Yes. Because tan inverse of root 3 is what?
It's
60 degrees, right? So this is 30. So we have 30 degrees. So the angle is 30 degrees, and since in the second quadrant, so we have what? What's our theta?
Yeah, it's 150.
Let's go down. This is 30 degrees.
degree.
210.
210 is in the third quadrant. Look at
That is 180 minus 10.
Yeah, 180 plus that. In the third quadrant, it's 180 plus
But it's in the second quadrant.
Then, second quadrant is 180 minus
Yes.
150. That is 150.
Now, if you look at this angle here, this is 90, this is 30, this is 60, right?
Yes.
So this is 2. Is that correct?
Which one?
No, I think 30 is good.
No.
Whichever way.
Okay.
See the same. 2 which one?
We have it this way, right?
Yes.
Okay, so here is 30, here is 60, here is 30. So here is 2, 2, 1, 1. This is what? 3. Right? So this is opposite over what? Adjacent. That's 60. 60, right? Then this is
1 over root 3.
opposite all over adjacent. That's 1 over root 3. So tan inverse of 1 over root 3 is 30 degrees. Right? Good. So it is 30 degrees. Then in the second quadrant,
It's 1 in the second quadrant, right?
yes,
It will be 150.
it will be 150.
So it's negative.
So we now have what? 150 degrees. Now we have our theta to be 150 degrees. So we then can say then we now have our z in polar form to be what? Z to be equal to what's our r? 2. Then open bracket cos 150 degrees plus what?
Right?
I sin what? 150 degrees. We have this. Now, therefore, z raised to the power of 8 will be what? 2 raised to the power of 8. Open bracket cos 8 times 150 plus I sin what? 8 times what? 150. So here we have 2 raised to the power of 8 is what? 64. Then open bracket cos 8 times 150. That's 800 plus 400. 1,200. So 1,200 degrees plus I sin 1,200. So this is the same as 64. Open bracket. This
Convert it to rand.
No, we can still convert it to rand, but we can still continue. We remember 1,200 degrees is same as 120 degrees.
Yeah, yes.
So which is cos 120 degrees.
It's about quadrant.
Yes. Plus I sin 120 what? Degree. Now what's the value of sin cos 120?
That is minus cos 60.
Minus cos 60. What is cos 60?
Cos 60 is
1
1 over 2.
1 over 2.
Yes.
Yeah.
You have your diagram here.
Yes, that is adjacent to hypotenuse.
Yes.
That is 1 over 2.
1 over 2. So minus 1 over 2 plus I sin 120.
That is
That is sin 60.
Sin 60.
Yes.
Which is what? Root 3 over 2. Root 3 over 2.
Yes.
So we have, then you open, right?
Alright.
So we have,
Yeah, sir. What if you find the LCM before you open?
all the same. This is 1, right? LCM is 2.
Yes.
This was the same thing. So we have 64. LCM 2, right?
Yes.
Minus 1 plus what? I root 3. Is that correct? This is what we have, right?
Yes.
64 by 2 is what?
That is a 32.
32. Open bracket minus 1 plus I root 3. So this is your final answer.
Okay.
So if you have this z, then 0 to the power of 8 is equal to this.
Okay.
So here, this is the final answer for 0 to the power of 8. Now, the B part, 0 to the power of 12. So we already have the polar form, right?
Yes.
So Z12 now will be what? 2 raised to the power of 12 cos 12 times 150, is that correct? Plus I sine 12 times 150. Ten times 150 is what? 1,500 plus 300, that's 1,800, right? So we have 2 raised to the power of 12 is what? 4,096. Open bracket. Cos 1,800 degree plus I plus I sine 1,800 degree. So this is the same as 4,096 plus how many of 360 can we find in 1,800?
This is 64 is 1,440.
Is that?
1,440. That's into 4.
Into 4.
Yes.
Into 5. What about into 5? It will be more than 1/8, right?
1,800 is sharp.
That is 5 times.
Is that?
5 times.
5
Right.
times.
Yes.
So, cos 0, right? Cos 1,800, what do you have? 1. Okay. Cos 0. So here will be cos 0. So actually this is 5 pi.
That means what are you? How are you?
This is 10 pi. Right? This is 10 pi. So that is 10 pi. Because 1 pi is 180, right? So this is 10 pi. So plus I sine 0 is what?
Sine 180.
Sine 1,800 will be what? Should be 0.
Should be 0.
Sine 0 is 0. So here is 0. So what we have now is 4,096.
1 plus 0.
1 plus what? 0. What is it? So we have 4,096. This is your final answer. We're trying to ask question.
Yes. How are you going to, you have 365 places. I mean, so how is it that you are going to say that 360?
This is it now.
Okay.
This is your quadrant, right? first, second, third, fourth. So this is 0, right?
Yes.
Now, so 360,
Yes.
right?
Yes.
Another 360,
2.
3, 4, 5. So it comes back to theta to be 0. Do you understand now? It comes back here, the fifth one, which is 1800 degree, and comes back to theta to be what? 0. Suppose we have 1860. Do you understand now? Suppose we have 1860. So what will happen now is this. The first, now how many of 360 do you have? 5. So as you count the 5, then we are left with what? 60. So you now move the 60. So it is now angle 60 you now take care of. So it means now that this angle is equivalent to angle 60 degree.
Okay.
So angle 1800 is equivalent to 0 degree.
So what if it is 4 times now? It will also be 0.
If it is 4 times.
Yes.
Whatever it may be.
Whatever remains.
If it is 4 times, like for example, you know this is 1,000.
Okay.
Let's assume we have 1,000.
Aren't you using it?
No, no problem. We'll go to LR1.
Okay.
Let's assume we have 1,440 here now. You know it goes there 4 times.
Yes. We are left with what?
0.
Okay, so suppose if we have 1,440.
Exactly, yes.
Yes, it will remain 0 degree.
Okay.
That is the meaning.
Okay.
Just like this place now. We go through this place almost 3 times. Then we are left with 120.
The remaining value is not
Okay.
So the remaining value is not to 360. So you will now find it.
I get it.
And since we are looking at about this angle and we want to use special angles to treat it, so
Okay.
we look at this one in the first quadrant and it's equivalent to the second quadrant. So that is why we are getting the value.
equivalent angle.
Equivalent angle. So we have our value to be this. So we can also do that for series to the power of 1.
I know mathematics, but this is Wahala.
So the C part, which is 0 to the power of -4, please do that and see what you have.
Alright.